guys, so today we're going to be going over this three-phase rectifier, full wave rectifier problem. And yeah, there's not exactly a way, if you just look at it, to tell whether it's RC, RL source, or just R load. So you have to be able to read the problem and understand what you're reading. It's not too difficult because it literally tells you, but be careful. Sometimes you can use the wrong equations from the crib sheet. Now, so let's read the problem. We're given this three-phase source of 240 volts RMS line to line. So that's kind of a mouthful. We can write this down. RMS line to line is equal to 240 volts RMS line to line, right? And we're also given the frequency at 60 hertz. And we're given the load. So RL load here is equal to 100 ohms. What else do we know? The load inductance is equal to 15 millihenries. So now it asks us for the average DC and RMS load current. So what does that mean? Average DC. So we have IO, that's the average DC, the output current. And we're also asked for the RMS load current. So IRMS, or more like IORMS, because O is for, you can technically think of that as load or the output, which is actually shown right there. Now, we need to find what IO is. This is where you look at your crib sheet and you figure out the equation. Make sure you're looking at the correct equations. IO is equal to this right here, if I can write on my screen, VO over R. So IO is equal to VO over R. Let's make sure to write this down so they know where we're coming from. VO, do we know this? No, we don't know this. VO is going to be equal to another equation given up here. VO is equal to 3 square roots 3 Vm over pi. 3 square roots 3 Vm over pi. Now, another problem comes up. Vm, we don't know this. We know VRMS load, or line to line. Now, how can we find, because we're not given, the relationship between line to line and phase or amplitude. What we have to do is we have to remember from, certain systems, or look at the crib sheet, maybe it has it on there somewhere. What we will know is V line to line RMS is equal to square root 3 Vm. Now it also has a second component, the RMS part. This is, remember, VRMS is equal to Vm over square root of 2. So we have to take this in square root of 2. This is something you just have to know. You can write this in your crib sheet for sure. I would recommend, because sometimes they might give this kind of value. We have to remember. Also, it doesn't matter which way you put the subscripts, it really doesn't matter. It means the same thing. So now we're gonna plug in, because we want to find Vm, right? So we have to kind of like rearrange the equation. Vm is equal to square roots 2 VLL RMS, V line to line RMS, divided by square roots of 3. And now we can plug that value in to Vm, and we can find V0. So now V0 is going to be equal to 3 square roots of 3 times square root of 2 VLL RMS, which we know to be, 240 from up here, divided by square roots of 3. You should see something that you can cancel. Of course, all divided by pi. We can cancel this square roots of 3. So now we have 3 square roots of 2 VLL RMS divided by pi. Remember, this is 240. I should have wrote this as 240 already, but this is going to be equal to about 324.11. Okay? Then remember, this is volts, not current. It's not amps. What we have to do is now we have to plug it back into the equation. I0 is equal to V0 over R. V0 is 324.11. Resistance is 100 ohms, meaning our current is about 3.24 amps. Awesome. Now, we are not done with part A. Remember, this is all part A. We need to find the RMS load current, IORMS. We're going to notice is using the equation for RMS values right at the bottom of the first part, we have to square and add and then take the square root of the DC current, or the average current, and the all the harmonics. So let's rewrite this equation, I naught squared, which is your average current, plus the summation of all the harmonics. And because this is a three-phase problem, we have to deal with 6, 12, and 18. Now, this is not, you're not going to have to do 12 and 18 in this problem, or most problems, because once you get to n is greater than or equal to 12, 18, so your harmonics are greater than or equal to 12, they become minuscule. They're very, very small, and they're irrelevant. An is irrelevant. So, now what can we do here? Well, we can say then the square root of I squared plus I6 squared over 2. Okay, so sorry, I moved a little bit. Hopefully y'all can't hear like the background or anything. So what we're going to end up doing is we're going to solve for I6 now because we have I0 here. We need to find I6. I6, we use an equation up here that has, let's see, In, right? We see the In, which is going to be this one here. It's kind of a long equation. So let's rewrite this, and then what I can do is I can copy and paste it down. All right, now that we have the equation, we can then plug in our values, right? So we want I6. So for every n, we're going to be plugging in 6. This is going to be equal to 6 square roots of 3. And remember, we don't have Vm. We have VLL RMS. So let's plug in that equation, square root of 2, VLL RMS, divided by square roots of 3, divided by pi times the magnitude of our impedance. So 100 squared, because that's our resistance, plus, and remember, every n gets the 6. 6 times 2 pi 60. Remember, omega is the angular frequency, meaning it's 2 pi times the frequency, times your inductance. So 15 millihenries, or 15 times 10 to the minus 3. And remember, we have to square all of this. Times 1 over 6 squared, because it's an n, which is 36 minus 1, or 1 over 35. And now what we can do is we can, again, see this square root of 3 cancels. This becomes 240. And we can then plug it into a calculator, and we're end up getting, it's about 0.13 amps. All right, so we can let this be 0.13 amps. And this can give you an idea about an idea about like what exactly this is an RMS. What am I talking about? A6. This can give you an idea about why we're not going to the 12th harmonic. If we went to the 12th harmonic, we're going to get microamps. We don't need that. So what are we going to get? We're going to get the square root of IO squared, which is 3.24 squared, and we're going to see it's not really going to make much of a difference. 0.13 squared minus over 2 is going to be equal to here. Again, it's equal to about 3.24 amps RMS. So what? That's our answer. We technically didn't even need to solve for the 6th harmonic, but we did, and we noticed it didn't make a difference. So now, for part B, it's going to ask us to find the average and RMS diode currents. Now, before we go and write that down, let's find out where those equations are. All right, so we see the average diode current and the average, and the RMS diode currents, which are right here. I'm sorry, let me get that better color. The average diode current and the average RMS diode current, or the RMS diode current. So let's write those down and we'll bring them down. And what are we going to notice? We already have these values. You notice we have 1/3 the average current, average load current. What is that? Well, we have it up here. It's going to be about 3.24 right here, 3.24 amps. So we're going to plug that into this equation, and we are going to get an answer. And for the RMS diode currents, we're going to do the exact same thing. Square root of 3 over 3 times the IO RMS current, which is what? 3.24 again? So now we'll plug this into our calculator, and we'll get an answer of 1.08 amps with our average diode current, and 1.87 amps RMS for our RMS current. It's kind of important, I would say, to put your units with RMS, if it is RMS, because remember, when we're dealing with RMS, and even in questions, sometimes, in other classes like energy conversion or circuits and systems, they don't give, sometimes they don't say it's RMS, but they assume it is. They assume you know. You don't want to be that kind of person. You're going to outright say what it is, because then you have them guessing, and then they're going to say, uh, they might give you the benefit of the doubt, which would be nice, but sometimes they're going to say, oh, you should be more explicit. They're going to take off points. There's no reason to lose points on something you got right. So, anyways, a little rant. Now, part C, the RMS source current. Let's look at the equations. What do we know? We're given the equation for RMS source current. This S means source. So we're going to take it square root of 2 over 3 IORMS. So this is part C. I source RMS is equal to square root of 2 over 3 IORMS. So what are we going to get? We're going to get the square root of 2 over 3 times the IORMS, which is 3.24. And when I plug that into my calculator here, we're going to get, sorry if my voice got a little bit quieter, I'm looking away now. We're going to get about 2.65 amps. And you can't forget amps RMS. You could even put SRMS if you want in there. Now, part D, it asks the input power factor. So, power factor. This is part D. What is power factor equal to? This should be the last equation down here, and it is. The input power factor is P, the power, real power, divided by the apparent power. And it actually gives us another equation. This is equal to the input power, or just the power, divided by square root of 3 V RMS times I RMS, I believe. I think it might be line to line, actually. Yeah, line to line and then source. So we're given the source current. We're given the line to line RMS current. I mean, we need power, though. What is power? How do we find that? Remember, power is the real power, right? So real power, what is that? Well, real power is going to be I squared RMS times the resistance. We do not add anything with inductance because inductance supplies, it supplies reactive power, right? So we divide that by the square root of 3 VLL RMS, which we remember to be 240, and I source RMS, which we solved in part C, 2.65. Now, IORMS, what is that? This is 3.24. 3.24 squared times the resistance is going to be 100 divided by square root of 3, 240 times 2.65. Now, for whenever we plug this into our calculator, we get about 0.955. And that's our final answer for power factor. I hope this problem was, helpful in being able to solve three-phase problems and understanding which equations to use. Because if you use the crib sheet and the exam review he gives, you're going to do just great. There's no reason to kind of panic about what could be on the exam. People in the past have said his exams are very similar to the exam review, so just go over the exam review, make sure you're comfortable looking through your crib sheet, because I know a lot of y'all's crib sheets, including mine, it has just a bunch of equations. So just get used to looking at it and knowing where everything's at. All right, so hopefully this helped. If you have any questions, oops, that's not right. If you have any questions, just let me know. All right, thank you all.